Hello everyone, welcome to my video on sigma notation. So a big part of calculus 2 is integration. So to understand integrals, they are defined as limits of Riemann sums. We understand the limits part, but we have to understand now the Riemann summation part. We're going to focus on the summation first. So when we're talking about finite sums, the symbols that we use is the Greek letter sigma, which is this symbol over here. And by definition, we say that if a subscript m, comma a subscript n plus 1 all the way to a subscript n are real numbers and m and n are integers such that m is smaller or equal to n, then the symbol we use is sigma with the index I. So we're starting at m. This is the starting point. We start at I, and we're going to finish at n. This is the n value of AI. So essentially what you're doing is you're substituting the I with the starting point, in this case m. So we have am. The summation symbol is telling you just to add. So we're going to add the next value. So the next value, add 1 to it. So that would give us a subscript n plus 1 plus a subscript n plus 2 all the way to the last value, in this case n, up until an. Always adding 1 to the index. And that gives us the summation, because mathematicians are lazy, or what I like to call efficient. So instead of writing 1 plus 2 plus 3 plus all the way to 1,000, this would take a really long time. We want a compact notation to express this, and that's why we introduce sigma notation, okay? So let's look at a couple of examples. So in this first example over here, it says to find the value of the sum. So let's start off with part A. We have the sum from I equals 1 to 4 of 3. So let's go ahead and find the value of the summation. Another thing I want to mention is that I'm using the letter I. You don't have to use the letter I. You can use any parameter you want. Typically use I, J, and K, sometimes N, but it really depends on the book you're reading. I'm typically going to use I, okay? So this one here is a bit of a trick. So we're taking the sum of 3. Notice there's no index I in the value of 3. So what this is really telling us is start at 3, and that's the first 3, and you're going to do that 4 times. But since there's no I, there's nothing to add 1 to, so you're just adding 3 4 times. You're starting at the first, second, third, fourth. We finish at 4. Okay, this gives us 3 plus 3 plus 3 plus 3, which is 6, 9, 12. And that's the value of this sum. Okay, let's look at, so this is a bit of a trick because you don't have the index I, so this value stays the same this many times. Let's look at B. So B, we actually have the index I in the sum. So we have the sum from 1 to 4 of I. What is this telling us? This is saying replace your I with 1, so we'll do that, plus the next value, you increase it by 1, so the next value is going to be 2, and the next one is going to be 3, and then we're going to stop at 4. Okay, we don't have to start at 1, but that's typical to start at 1 or 0, but you can start at any value you want here. So this means 1 plus 2 plus 3 plus 4, so that's 3 plus 3 is 6 plus 4, that's 10. And that's the value of this sum. Let's keep practicing. So in this example over here, for C, we have the summation from j equals 2 to 5. So now we have the letter j that we're using instead of I of j squared. So now you should have a better feel for summation. So pause the video, try to see if you can get this on your own, and compare your answer with mine. So the index is starting at 2, so we're replacing the j with 2. So we get 2 squared plus, since the j's on the base, it's the base that's changing, that we're adding 1 to. So the next value is 3 squared. The next one's 4 squared. And then we end at 5 plus 5 squared. Okay. 2 squared is 4, plus 3 squared is 9, plus 4 squared is 16, and 5 squared is 25. 4 plus 16 is 20, 20 plus 25 is 45, plus 9 is 54. So the value of the sum is 54. Okay. Let's move on to D. D, we have k equals -1 to, oops, I forgot the upper term. Let's put a 1 here. Let's go from -1 to 1. So we start, first of all, we're using the parameter k, and here we have the value -1. We're starting at a negative value. As long as this value is smaller than this, it's fine. So let's substitute our values in. Replacing k with -1, we get 1 over -1 plus 2, plus 1 over 0 plus 2, and then we end at 1 plus 1 over 1 plus 2. So this is just negative 1 plus 2 is 1, so we have 1 over 1, plus 1 over 0 plus 2 is a half, plus 1 over 1 plus 2 is a third. Okay, so we just have to find a common denominator. In this case, it's 6. So we get 6 over 6 plus, we multiply the top and bottom by 6, multiply the top and bottom by 3, 3 over 6, and multiply the top and bottom by 2, 2 over 6. Now that the bases are all the same, we can add the numerators. So 6 plus 3 is 9, plus 2 is 11, and the base stays the same as 6. And this is the value of this sum. So this next example is a nice one. Try it on your own, see if you can get it. We're taking the summation starting at 1 to 4 of 1 over 1 plus I minus 1 over 2 plus I. So pause the video, try to see if you get the same answer as I do. So we start off by substituting the i's with 1. Let's do it down here just to give myself some room. So we have 1 over 1 plus 1 minus 1 over 2 plus 1. Okay, this is the first bracket. The next one we have is, we're going to replace it with 2. So 1 over 1 plus 2 minus 1 over 2 plus 2. So we're substituting all the i's with 2's. Let's put this in brackets just to make it a bit more apparent. Now we're substituting all the i's with 3's. 1 over 1 plus 3 minus 1 over 1 plus, 2 plus 3. And I'm just going to add the last one here, giving us 1 over 1 plus, we're stopping at 4. So 4 minus 1 over 2 plus 4. Okay. So this is the case 1, 2, 3, 4. We're adding them up, and this is our setup. So let's go ahead and solve this. So the first bracket over here, we have 1 over 1 plus 1, which is a half, minus 1 over 2 plus 1, which is a third, plus a third minus a fourth, plus, in this bracket up here, a fourth minus a fifth, plus the last bracket here, a fifth minus a sixth. Okay. So this is what we have. What you have to catch, and this is what's nice about this example, and this is something that's going to show up later in the semester, is instead of finding a common denominator with all these values, what you can notice is that over here, the second term and the third term, it's the exact same value, opposite sign. This is negative a third, this is positive a third. These guys cancel. And similarly here, we have negative a fourth, positive a fourth. Same number, opposite sign, they cancel. And same thing over here, negative a fifth, positive a fifth. Same number, opposite sign, they cancel. Leaving us with the first term and the last term. This is called telescoping method. So basically everything in the middle collapses like a telescope. Okay, and you're left with the first and the last term. It won't always be the first and the last term. There's going to be different variations depending on the sum. But this is the idea where everything in the middle is cancel when they have the same value, opposite sign. So keep this in mind because this is really important. So we're left with a half minus a sixth, 1 over 6. And we could go ahead and find a common denominator here, which is 6, multiplying the top and bottom by 3, giving us 3 over 6, minus 1 over 6, which is 2 over 6, which gives us a value of a third, and that's the sum. Okay, so very important example. Keep in mind telescoping sums. It's going to come back later in the semester. Okay. So in the next example over here, we have to express the sums using sigma notation. So they write it in this form, and we're going to express it using the sigma notation. So we have 2 to the 4 plus 3 to the 4 plus 4 to the 4 plus 5 to the 4. How do we express it as a sum? So the first thing you have to catch is what's changing and what's not. Notice that the exponents are all 4. So I'm going to start with the index I, and I know that the exponent of whatever I have in here stays as 4. Okay, because all of them have the exponent 4. That's good. And I notice that 2, 3, 4, 5, the base of the exponents are all changing. They're increasing by 1. That's good news. So I'm going to call this some letter I. The index I'm using is I. Okay, so it's going to be I to the 4. And what's my starting value? Well, my starting value is the first term. We're starting at the value 2. So I'm going to start at 2. And what are we finishing at? Well, it stops at 5. So the sum ends at 5. So this is this expressed in sigma notation. Okay, so this is the form. Notice that this isn't the only possible solution. I could have started at 1, let me write it down here. I could start at I equals 1 and finish at 4 and write I plus 1 to the 4. Notice that this would also provide me with this this form, because if I start at 1 here, I plus 1 or 1 plus 1 is 2 to the 4, which is my first term. Then the next one would be 2, so 2 plus 1 is 3, 3 to the 4, that's the next term. 3 plus 1 would be 4 to the 4, that's the next one, and then I stopped at 4, so 4 plus 1 is 5 to the 4, which is my last term. So these are equivalent. So there's more than one way to express your answer using sigma notation. There's not only a single solution. Okay. So if you get an answer that's similar to mine or it looks different, it might still be correct, not just what I'm doing on the board here. So another thing here, if we look at B, we have 4 plus 5 plus 6 plus 7 all the way to n. It's going up by 1. It's starting at 4 and it finishes at n. So we could express this as a sum starting with using the index I starting at 4. So I'm going to start at 4 and finish at n. Okay, and we know that it's going up by 1. So that's perfect. I'm just going to use I. Because the first term is going to be 4, the next one's going to be 5 plus 6 plus 7 all the way to my last term n. And we're done. This is the sigma notation for this form. Okay, let's keep practicing. So in this next example over here, try this on your own, see if you get it. In my opinion, these are slightly more difficult, and if you have the sum, you have to expand it out, whereas here we have to work backwards and find the sum. Finding the pattern is a bit more work, I find. But let's start off with C. This shouldn't be too bad. Pause the video, see if you get it. Right now, expressing this as a sum, I'm using the index I. And what are we starting at? Well, we have 0, and the next term is not 1, it's 2, so it's going up by 2. So we have to keep that in mind. So we're starting at 0, and we're finishing at 2n. Okay. So one way of doing this is you could factor out a 2, in a sense. So it's going to be 2 times, this isn't the only way of doing it, that's just the way I'm seeing it now. Factoring out a 2, you get 0 plus 1 plus 2 plus 3 plus n. And this is pretty much the example we saw earlier. So it's 2 times whatever we have in here. So we have the sum starting at 0, it's going up by 1, and it's finishing at n. Okay. And since we have a 2 sitting in the front, we could put a 2 over here. Okay. So this is one way of expressing this summation. So 2 times the sum from starting at 0, finishing at n of I. Okay. Another way is if you would have just done it, notice that it's going up by 2, you could have just written 2i here. Doesn't matter. So the 2 essentially doesn't affect the sum, it could be pulled out of the sum. So if you wrote it this way, 2i, that's fine as well. That's another way of representing this summation. Okay. So that's one possible solution. Let's look at this one. This one here, D, is a lot more difficult, so try to find a pattern in here. So pause the video, attempt this on your own. So 1, I like to think of it as 1 over 1, and I like to focus on the numerator and the denominator individually. This is my my advice. So if I look at the numerator, I have 1, 2, 4, 8, 16. There's a pattern that emerges here. 1, 2, 4, 4 could be written base 2, 8 could be written base 2, 16 could be written base 2. So I could think of this as the numerator as 2 to the 0, 2 to the 1, 4 could be expressed as 2 to the 2, 8 could be expressed as 2 to the 3, 16 could be expressed as 2 to the 4. And same argument with the base. We have 1, 3, 9, 27, 81. These are all powers of 3. So I could represent 1 as 3 to the 0, 3 as 3 to the 1, 9 as 3 squared, 27 3 cubed, and 81 is 3 to the 4. Okay. And notice now, this whole thing could be rewritten as 2 over 3. Since they have the same exponents, it's all that to the exponent 0. Plus 2 and 3 here both have exponent 1, so we can rewrite it as 2/3 comma exponent 1. This doesn't change. Instead of writing 4 over 9, we could write it as 2/3 to the exponent 2, 2/3 exponent 3, and 2/3 exponent 4. And expressing it this way, now it's easier to write it as a sum, because this is the sum starting at, the base here doesn't change, it's always 2/3, so I'm going to keep 2/3 over here. The thing that changes is the exponent. It's going up by 1, and it's starting at 0. So I'm going to start at 0, and I'm going to change the exponent. That's the thing that's changing, so I'm going to call it I. And when do we stop? Well, we started at 0 and we stopped it at 4. And this is the final answer. Okay. So here we introduce an important theorem of all these properties that we have to have memorized. So I'm not going to prove it, I'll prove it in a different video, but for now you just have to make sure that you have all these properties memorized. So first, if c is a real number and n is a positive integer, then the first property that we have, and we actually saw this already, is if we take the sum from I equals some value to n of c times ai, you could, if you have a constant c, you could essentially pull it out of the sum. So we saw this with the example with the 2. The 2 could have been expressed inside the sum or outside the sum, it doesn't matter. And this is what the property is telling us. So if you have a constant, you could essentially remove it from the sum. So you have the constant on the outside, and we have the sum I equals m to n of ai. So that's the first property. Make sure you have this memorized. The next property is that if you have a sum of two terms which are being added or subtracted, so the sum is from m to n of ai plus or minus bi, then you could express them individually. So you could take the sum of ai from m to n and add it or subtract it, depending on the case, to the other sum of bi. Okay, so you could take the sum of each term individually. That's what that's telling us. 3 to 7 has to be memorized. These are very common exam type questions that are given, and these properties are often, students are often forced to memorize these equations over here. So the third one and the fourth is essentially the exact same one, so you don't really need to know the third, you really need to know the fourth. What this is telling us, if you have the sum specifically from 1 to n of just the number 1, that's equal to n. This is telling us you're just adding 1 plus 1 plus 1 plus 1 n times. So essentially what we're doing is we're multiplying the 1 times the n over here, giving us n. Same thing here. You have the I from 1 to n. Notice again, both these examples here, there's no I in the sum. They're giving us values, constants. So this doesn't change. So you're adding c plus c plus c plus c plus c n times. So the answer is just c times n. Okay. This is just a special case where the constant is 1. So if c is 1, 3 and 4 are identical. Okay, so just memorize 4, that's good enough. The 5th, 6th, and 7th, you guys definitely have to know these. The 5th one is saying that the sum from 1 to n, notice that we have an I now, is equal to n times n plus 1 divided by 2. So this just has to be memorized. The 6th, the sum from 1 to n of I squared now. So we did I, we have I squared. This one's the one that students have like the most difficulty remembering. It's n times n plus 1 times 2n plus 1 divided by 6, so make sure you have this memorized. And then the final one that we deal with is the sum from 1 to n of I cubed. So we deal with I squared, and I cubed. And I cubed, I specifically put it in this form because it helps me memorize, because I cubed and I are very similar. Notice that we have the n times n plus 1 over 2, all that squared. It's the exact same thing as here, but the added fact that we're squaring it. Okay, so I put it specifically in this form just to remember it, just because it's easier to memorize this way. So I keep it in this form, n times n plus 1 divided by 2, and for I cubed, we just square it. So that saves me 2 of them, that's easy to remember. It's really just equation 6 over here that we have to have memorized. So we're going to use this to solve a couple of examples. So make sure you take a screenshot if you have to. Make sure you have these written down, and we'll apply them in examples now. So in this example over here, it says to find the value of the sum, and the first example we have is the sum from 1 to 12 of 3. So essentially what we have to do here is add 3 12 times. But using our property, we know that the sum I equals 1 to n of c times n, of c is equal to c times n. So if you have a constant, then you're just multiplying the constant by whatever number is up here, starting at 1. We're starting at 1, we're good. So what we're essentially doing here is just multiplying 3 times 12. So instead of adding 3 plus 3 plus 3 12 times, we know this is just 3 times 12, which is 36. Okay. So we're using this property here that we saw earlier. So c times n, 3 times 12, and we're done. Okay. So we could use our theorem just to simplify our the problem for us. Let's look at the next one. Now we have I from 1 to 50 of I. Well, how are we going to do this? What this is telling us is to add 1 plus 2 plus 3 plus 4 all the way to 50. That would take a really long time, especially if you don't have a calculator. But what we could do is just apply the property that sum of I from 1 to n is equal to n times n plus 1 over 2. So all this is really telling us is substitute into this formula the n, the upper bound, which is 50. So we're going to have really, this is just 50 times 50 plus 1, oops, 50 plus 1 over 2. So this is just 50, well, 50 divided by 2 is 25. And 50 plus 1, so 25 times 51, which we could do by hand. 51 times 25, 5 times 1 is 5, 5 times 5 is 25, 2 times 1 is 2, and 2 times 5 is 10. So this gives us 5, 7, 2, 1. So this is 1,275. And that's the final answer. Okay. So this is a lot easier than having to add 1 plus 2 plus 3 plus 4, so on and so forth. So using our properties is useful. Let's take a look at a couple of harder examples. So in this next example over here, we have the sum from 1 to n of 2i plus 5. So notice now we don't actually have a value on the upper bound. We have n. So how do we deal with that? So again, here we have no choice to apply our properties. So we could first use the property that if we have the summation, we could deal with them individually. So this means that we have the sum I equals 1 to n of 2i plus the sum I equals 1 to n of 5. And we know if we have a constant inside, we could pull it out. So we could go ahead and rewrite this as 2 times the summation I equals 1 to n of I plus the summation of I equals 1 to n of 5. Okay. And now these two pieces here are properties that we know. This is property, I believe it was 4, where you have a constant times the n. So this is just simply 5n. And this piece here, the 2 is a constant, so we'll leave it. But the summation from 1 to n of I, we know is the formula n times n plus 1 divided by 2. So we're expressing it solely in terms of n's. There's no i's anymore, there's no summations. And now we know the 2's cancel here. And we're left with n times n plus 1, giving us n squared plus n plus 5n. This is n squared plus 6n, which we could write as n times n plus 6. And this is our final answer. Okay. So this is an example where we have to apply our properties in order to simplify it in this form. Okay. So whatever the upper bound is here, n, let's say it was 40, we could just directly substitute it into here. So in this next example over here, we have the sum from 1 to n of I squared times I minus 1 plus I. So let's go ahead and solve this. Again, pause the video, try this on your own, see if you're able to get it. The first thing I would do is distribute the I, giving me I cubed minus I squared plus I. And now, since we have an addition and subtraction, we'll take the sum of each term individually, giving us the sum I equals 1 to n of I cubed minus the sum I equals 1 to n of I squared plus the sum I equals 1 to n of I. Okay, and now we apply our properties in here. So we know I cubed, we know the formula for I squared, and we know the formula for I. This gives us I cubed was n times n plus 1 over 2, all this squared, minus I squared was n times n plus 1 times 2n plus 1 over 6. And the last one is I, which is plus n times n plus 1, all that over 2. Okay, so we substituted all the terms. Now we just have to find a common denominator. Could we factor anything out? I would factor out the n plus 1 first, giving us, and maybe over 2. I'll take out the 2 as well. So let's factor out an n plus 1 over 2. And here, if we take out an n plus 1 over 2, we're left with an n squared, because remember, the whole thing is squared. And the n plus 1 is also squared. So if we took out 1 and squared, we're left with just one of them, n plus 1, over the 2 is out, but remember, it's squared. So really on the bottom, we have a 4. And if we take out a 2, we're still left with another 2. Minus, here we took out n plus 1 over 2, so we're left with an n. We're left with a 2n plus 1. And we're left with, if we took out 2 from 6, we're left with 3. Plus, here we took out an n plus 1 over 2, leaving us with just n here. So we took out the n plus 1 over 2, but we still have to simplify all this. We could go ahead and find a common denominator. Is there a better way? Oh, we could take out an n as well. Let's go ahead and factor out an n. Each term has an n. So, factoring out an n, this leaves us with n over here, this n is gone, and this turns into a 1. Okay, that's a bit easier. So let's go ahead and find a common denominator. We'll make it to be 6. So what we have here is n times n plus 1 over 2. Here I'm going to just distribute. Well, let's first find a common denominator. Here we have to multiply the top and bottom by 3. So we get 3n, n plus 1 over 6 minus, here we have to multiply the top and bottom by 2. So 2 times 2n plus 1 over 6. And here we have to multiply the top and bottom by 6. So plus 6. Okay. So all we have to do is really factor out, we have to just distribute the top over here. So I'm just going to erase the top to give myself some room. Up here. And we're going to continue from this point on. So here I'm just going to factor out the 6 on the bottom. So we have n plus 1. And then here we have 2 times 6, which is 12. And what are we left with in here? So we're left with 3n times n, which is 3n squared. 3n times 1 is 3n. Negative 2 times 2n is minus 4n. And then minus 2 times 1 is minus 2. And then plus 6. Okay. So here we could simplify, combine like terms, giving us n plus 1 over 12. And in bracket here, 3n squared minus n plus 4. Okay. And could we factor this? If we do product sum here, we're looking for two numbers that multiply to give us 12 and add to give us negative 1. Let's see if we could simplify further. This could be 3 and 4. We can't get negative 1. 6, 2. No, this doesn't work. We can't get a negative. Yeah, so we leave it like this. This is the final answer. Okay. So in this next example over here, you have to find the value of the sum, and the sum that's given is the sum from 1 to 50 using the index I of 3 to the I minus 3 to the I minus 1. So pause the video, try to see if you can solve this on your own. How would I go about this? So the fact that I see a minus, I'm thinking that my first instinct is telescoping. Whenever I see a fraction, two fractions being subtracted, or if I see two terms being subtracted, my first instinct is to use telescoping sums. Okay. You could, if you attempted to solve the sum individually, that's a good attempt as well, but then you lose the sum and it becomes difficult because we don't really know how to deal with 3 to the I. So let's go ahead and start substituting the first couple of values in just to see what we get. So if we substitute the 1, we get 3 to the 1 minus 3. 1 minus 1 is 3 to the 0. Plus the next one, if we substitute 2, we get 3 to the 2 minus 3 to the 1 plus dot dot dot. Let's do the last couple, or maybe let's do a couple more. Just make it a bit more obvious. So we did 2, let's do 3. We get 3 to the 3 minus 3 to the 2 plus dot dot dot. And then I'm going to do the last 3. So I'm going to continue down here. The last 3 would be 48, 49, 50. So if I do 48, we have 3 to the 48 minus 3 to the 47 because you subtract it by 1. Now I'm going to do 49. So 3 to the 49 minus 3 to the 48. And then 3 to the 50 minus 3 to the 49. Okay. So by expanding it, hopefully you see a pattern that emerges. So what I notice is 3 to the 1 here is positive and 3 to the 1 here is negative. Same number, opposite sign. So I know this one's going to cancel with this one. Okay. So notice that in two adjacent brackets, let's say, the first and the last term cancel. Okay. Now, if we look at the next bracket, 3 to the 0, there's no other 3 to the 0, so I can't deal with that. But we have 3 to the 2. There's one that's positive, one that's negative. Same number, opposite sign. They cancel. And now the 3 to the 3 is positive here, but I didn't write it, but we know the next bracket that's going to contain on the outside a negative 3 to the 3. That's going to cancel with something in here. Okay, so we're just left with this first term. And then we continue with this pattern. If we look at the end, this is where I wrote the last three. If you're not convinced, expand it further to convince yourself. Maybe go up to 4 or 5 and take the last 4 or 5 terms, and you'll see the pattern continues. But here, if we go to the end, notice again, on the outside of the brackets, 3 to the 49 positive, 3 to the 49 negative. These guys cancel. So again, on the outer brackets, these guys cancel. 3 to the 50, there's only 1. So I can't cancel that. If I go to the next bracket, notice the 3 to the 48 cancels with the negative 3 to the 48. And again, the negative 3 to the 47 would have canceled with something that was over here. I didn't write it out, but you could expand it yourself if you want to convince yourself. So this would cancel with a term over here, and everything in the middle would cancel out and eventually collapse, leaving us with negative 3 to the 0 and 3 to the 50. Notice that it's not the first and the last term. The last time we saw a telescoping series, it was the first and the last. But this is an example where it's not the first, it ends up being the second term and the second to last term, leaving us with negative 3 to the 0 plus 3 to the 50. And we know 3 to the 0 is just 1, so this is just 3 to the 50 minus 1. And that's the value of this sum. Okay, so telescoping series, very important. This is a nice example. So whenever you see a subtraction of, especially fractions, that's usually the giveaway. Subtraction of fractions or a subtraction between two terms, think about telescoping sums, okay? So the next example over here says to find the value of the limit. That's right, limits are back. So we have the limit as n tends to infinity of the sum from 1 to n of 2 over n times times I over n, all that squared. So let's go ahead and solve this. The thing you have to remember about limits is that the limit as n tends to infinity, we saw with x's, if you have a number over n, as n gets really large, so you're dividing a number by infinity, this goes to 0. The other thing to remember is that if the exponents are the same of the numerator and the denominator, let's say you have limit as n goes to infinity of n squared, 1n squared over 2n squared plus 3, let's say. You look at the highest exponents, it's a 2, it's a 2. The answer for this limit is 1/2. Okay. You take the coefficients of the numbers with the highest exponent, okay, in the numerator and denominator. When they match, when they're equal, the answer is just the coefficient, so this is 1/2. Okay, so this is a trick. If you forgot this, there's a video on this. You can go back and look at that, and where it tells you all the tricks. But typically, it's the one with the same exponent. That's what we usually get. Okay, if not, the exponent on the bottom is larger, which means it goes to 0. Okay, so just keep this in mind. So let's go ahead and evaluate the limit. So we'll kind of ignore the limit for now, but the limit is talking about n, right? Here we have a sum starting at I. So all the n's inside the sum, you could treat them as a constant and pull them out. So we could write this as the limit as n goes to infinity of the summation of I equals 1 to n of 2 over n times I squared over n squared. Okay. So all I did is I distributed the square. This is property laws of exponents. And then the sum, I'm going to take out the n squared and combine it with this. Treat it as 2 over n cubed times I squared. So notice that I'm kind of singling out the I squared. Anything that has an I, we have to keep it in the sum. Anything that doesn't have an I, we could pull it out of the sum because we could treat it as a constant. This is just some value, it's a number. We're going to pull this out of the sum. We don't have to worry about it. So what we get is the limit as n goes to infinity. In this case, we have 2 over n cubed. That's pulled out, and it's leaving us with the sum I equals 1 to n of I squared. Okay. And this is a property that we know. These are the formulas that we have to have memorized. So we could rewrite this in terms of n, giving us, let me do it up here, limit as n goes to infinity, 2 over n cubed, and for I squared, the property is n times n plus 1 times 2n plus 1, all that over 6. Okay, so we don't have any summations anymore. Now we're just dealing with the limit of this. So let's go ahead and simplify this and take its limit. So if we look at the numerator, here we could cancel out 1n with the n cubed, leaving us with n squared, and 2 over 6 becomes a third. So we could rewrite this as the limit as n tends to infinity of n plus 1 times 2n plus 1, all this over 3n squared. Because 2 over 6 is 1/3, so we're left with a 3 on the denominator and the n squared because the n's cancelled. Okay, so next we could distribute the numerator, leaving us with the limit as n goes to infinity. N times 2n is 2n squared. n times 1 is n, 1 times 2n is 2n, and 1 times 1 is 1, and on the denominator we have 3n squared. Okay. Now we use the property that we saw earlier, where if the highest exponents are the same, which in this case they are, we have n squared and n squared, then we just take the coefficients in front. So the answer here of this limit is 2 over 3. Okay. You could take the limit as n goes to infinity of each term individually, or divide or factor out the numerator and the denominator by n squared. That's another way of doing it, but I'm okay with this shortcut, seeing that these problems get long. So you can use the fact that if the exponents are the same, the answer is the coefficient. Okay, let's take a look at our final example. So in this next example, again, we have to find the value of the limit. So we have the limit as n tends to infinity of the sum of 1 to n of 2 over n times, in brackets, 2i over n all that cubed plus 5 times 2i over n, close bracket. So pause the video, try to solve this on your own, see if you're able to solve it. So the first thing I'm going to do is distribute, giving us the limit as n goes to infinity of, let's keep the summation and the 2n on the outside. Okay, and we have 2n, open bracket, I'm going to distribute the cubed, giving us 8i cubed over n cubed plus 10i over n. Okay, so we're just simplifying here. Now I'm going to distribute the 2n. Should we distribute or factor out? Let's distribute. And we'll deal with each term individually. So I'll factor in, I'll distribute the 2 over n, giving me 16i cubed over n to the 4 plus 20i over n squared. The reason why I'm doing this is because I'm going to take the sum of each term individually, seeing that I couldn't factor out a common term. So we get the limit as n goes to infinity, sum I equals 1 to n, and we'll take the sum of this term first. So 16i cubed over n to the 4 plus, and now I'm going to take the sum of this term individually, 20i over n squared, sum from 1 to n. Okay. And now I'm going to deal with each term individually. I'm leaving the limit in the front. And I'm going to take out everything in this first sum that doesn't have an I involved, because everything else that doesn't have an I is treated as a constant. So we'll pull out the 16 over n to the 4, leaving us with the sum I equals 1 to n of I cubed. Okay. And the second summation, what we have is we'll factor out the 20 over n squared plus 20 over n squared, and we're leaving the sum of I. Okay, so these two terms, we know the property, so we're going to convert this using just n's, leaving us with the limit as n goes to infinity, 16 over n to the 4, and we know this could be written as n times n plus 1 over 2, all that squared, plus 20 over n squared, and we know this is just n times n plus 1 over 2. So these guys have to be memorized. So next what we have is we could start simplifying these. So 16 divided by 2 is 8, but it's squared, so it's technically 4. So we have the limit as n goes to infinity. 16 over 4 is just 4. Here it's n squared, here it's n to the 4, leaving us with an n squared on the bottom. Because we distribute the square here on the n squared, we'll cancel this with 2 of them down here. And then we're left with an n squared, n plus 1 squared here. Okay. Plus, and now we'll take the limit of this term as well. Limit as n goes to infinity. 20 divided by 2 is 10, and one of the n's cancel here, leaving us with 10 n plus 1 over n. Okay. Let me just erase to give myself a bit more room. So I'll come back up here. At this stage here, we're taking the limit as n goes to infinity. We could factor this out, leaving us with 4 n squared plus 2n plus 1 by distributing n plus 1 times n plus 1. Remember, it's a binomial, so we FOIL over n squared, plus the limit as n goes to infinity. And here we have, I'm going to distribute the 10, so we have 10n plus 10 over n. Okay. And on top over here, we could distribute the 4, giving us 4n squared plus 8n plus 4. So I distributed the 4 in the front. And again, we use the same property. The fact that the largest exponent of the numerator and denominator is 2, we take the coefficient in front. So here the limit is simply just 4 over 1, which is 4. And here the highest exponent is n to the 1, n to the 1. So we take the coefficient of the n, leaving us with the 10. So it's 4 plus 10, leaving us with the final answer of 14. So I hope this video helped. I hope you understand limits and summations better, and I'll see you in the next video.